When we think of the most terrifying objects in the universe, one name usually comes to mind first: the black hole. A place so dense, so powerful, that not even light can escape. A region of space where matter collapses into itself and the rules of physics bend under pressure. It sounds like the very definition of a cosmic monster. But what if there is something even more unsettling than a black hole? For centuries, human fear has often been directed at the known: earthquakes, storms, predators, even cosmic dangers like comets, supernovae, or gamma-ray bursts, however destructive, at least follow recognizable patterns. Science can model them, predict their behavior, and give us a sense of order. But what if there is something that refuses to fit any model? A phenomenon so extreme that it strips away every law of nature we've ever discovered? That is where the idea of the quantum singularity enters. It is not simply a region of space, not a star, not a planet, not even a black hole in the ordinary sense. It is a point of complete uncertainty, a place where Einstein's general relativity, the theory that explains the vast cosmos from planets to galaxies, collides head-on with quantum mechanics, the theory that governs the microscopic world of particles and atoms. Both theories are accurate within their own realms, yet at the singularity, they contradict each other. In such a place, space and time themselves lose their meaning. Distances collapse, time intervals vanish, and the very idea of cause and effect breaks down. It is as if reality itself reaches its breaking point, like glass shattering under too much pressure. From the earth beneath our feet to the farthest galaxies, every law of nature that guides the cosmos stops working there. This is not a comfortable thought. We are used to danger being measurable: the speed of a hurricane, the magnitude of an earthquake, the mass of an asteroid. When something can be measured, it can be understood, and in a way, that brings comfort. But what about something that defies all measurement? What about a place where we cannot predict what will happen because the very framework of prediction fails? That is what a quantum singularity represents. And that is why, in the deepest sense, it may be the most frightening concept science has ever proposed. The paradox only deepens when we remember that the universe itself, everything we see today, may have begun from exactly such a singularity. According to the most widely accepted cosmological model, the Big Bang did not start from a large fireball in space, but from a state of unimaginable density and energy compressed into a single point, a quantum singularity. From that singularity came every star, every planet, every atom in your body. In other words, everything around us may be the children of a singularity. And yet, this is not just ancient history. These singularities are not locked in the past. They may still exist today, hidden inside the dark hearts of black holes. The idea that such a mystery still lurks in the universe, invisible, silent, perhaps countless in number, is what makes this subject so compelling and so unsettling. So, if black holes are already terrifying, what does it mean that something even more extreme might be waiting inside them? How can we even begin to understand what lies beyond the event horizon? To understand why a singularity is so mysterious, we need to break it down step by step. First, let's look at the two great pillars of modern physics: Einstein's general relativity and quantum mechanics. General relativity describes how gravity shapes the universe. It explains how planets orbit stars, how galaxies form, and how space itself bends around massive objects. Whenever we look up at the night sky and see the dance of celestial bodies, it is relativity at work. Quantum mechanics, by contrast, describes the smallest scales of reality. It tells us how electrons move around nuclei, how particles pop in and out of existence, and how the building blocks of matter interact in ways that often seem counterintuitive. Whenever your phone screen lights up, or a computer chip processes information, it is quantum mechanics that makes it possible. Both theories are incredibly successful in their domains. Relativity handles the vast, quantum mechanics handles the tiny. But at a singularity, these two theories collide, and the result is chaos. Imagine compressing matter so tightly that it no longer behaves like matter. At densities approaching infinity, relativity insists that gravity grows without limit, pulling space and time into a single point. Quantum mechanics, however, forbids absolute certainty at such scales. The uncertainty principle, the rule that says you cannot know a particle's exact position and momentum simultaneously, begins to dominate. Instead of a clear solution, physics gives us contradictions. This is what we call a quantum singularity, a hypothetical point where our best theories break down. Inside it, space and time lose their ordinary meaning. Distances shrink to zero, time intervals vanish, and mass becomes infinite in theory. Our most trusted laws no longer apply. In effect, reality becomes undefined. This is not just speculation for the sake of mystery. The Big Bang model itself begins with a singularity. When cosmologists wind back the expansion of the universe, all of space, all of time, all of energy converge on a single state of incomprehensible density. At that point, general relativity predicts an initial singularity. Quantum physics, however, suggests that conditions were so uncertain, so unstable, that a fluctuation could have sparked the expansion we now call the Big Bang. The idea is profound. The entire universe, stretching billions of light years across, may have once been compressed into something smaller than a subatomic particle. And at that moment, the rules of physics did not just bend. They disappeared. What makes this idea even more disturbing is that singularities are not limited to the birth of the universe. They are still with us today, hidden inside the cores of black holes. Every time a massive star collapses beyond a certain threshold, gravity crushes matter beyond recognition, and according to relativity, it continues to collapse until it forms a singularity. But is this singularity the same as the one that created the universe? That remains an unanswered question. It is possible that singularities inside black holes are different, confined to those cosmic prisons, never escaping. It is also possible that they are windows into something deeper, points where our universe connects with something beyond. Astronomers and physicists wrestle with these questions because they strike at the very foundations of reality. We want to know, do the laws of nature truly end at a singularity? Or is there a deeper theory, still undiscovered, that unites relativity and quantum mechanics into a single framework? This search has a name: the quest for quantum gravity. It is one of the greatest unsolved problems in science, and black holes, the most extreme laboratories of nature, may be the only places where we can look for answers. So, if a singularity is the ultimate breakdown of physics, where do we find them? The answer lies inside the darkest objects we already know: black holes. If singularities are the most mysterious objects in physics, then black holes are the doors that hide them. To understand what might be waiting inside, we first need to ask, what exactly is a black hole? A black hole begins as ordinary matter. But if too much mass is packed into too small a volume, gravity wins. At a certain point, no known force can resist the collapse. Electrons are forced into protons, forming neutrons. If collapse continues, even neutrons cannot support themselves. Eventually, matter compresses beyond recognition. At that boundary, something remarkable happens. The escape velocity, the speed needed to break free from gravity, becomes greater than the speed of light. On Earth, the escape velocity is about 11 kilometers per second. From the surface of the Sun, it is about 600 kilometers per second. But at a black hole's event horizon, the escape velocity exceeds 300,000 kilometers per second, faster than light itself. And since nothing can outrun light, nothing can escape. That's why the black hole is truly black. It emits no light of its own. No signal can leave once it crosses the horizon. From the outside, we see only darkness. But this darkness is not empty. Matter in the surrounding region spirals inward, forming what astronomers call an accretion disk. Particles are accelerated to near light speed, colliding violently, heating to millions of degrees, and radiating high-energy X-rays. This glowing halo is often the only sign that a black hole is there at all. The drama doesn't stop there. As matter crosses the event horizon, it is lost to us forever. From the outside, it seems to slow down, frozen at the edge, fading into redder and redder light. From the inside, time for that matter effectively ends. The closer you approach a black hole, the stronger this warping of time and space becomes. It is here, at the heart of the black hole, that general relativity predicts the inevitable. The collapse continues until everything is squeezed into a singularity, a point of infinite density, where the laws of physics no longer apply. This is why many scientists consider black holes to be natural laboratories for singularities. We cannot see inside them, but we know, or at least our equations suggest, that at their centers, the most extreme conditions in the universe are taking place. To put this into perspective, imagine a black hole the mass of our Sun. Its event horizon would be only about 3 kilometers across. That's smaller than the size of a large city. Yet within that space lies the full mass of the Sun, compressed into an unimaginably small volume. Now, imagine a black hole, millions or even billions of times the mass of the Sun, the kind we find at the centers of galaxies. Each one is a possible gateway to a singularity, hidden behind an invisible wall. Astronomers cannot observe singularities directly, but by studying the environment around black holes, they can infer their presence. The way matter orbits, the energy emitted in X-rays, the jets of plasma blasting outward at near light speeds. All of these are fingerprints of black holes feeding on their surroundings. So when we ask where singularities might exist today, the answer is simple: inside black holes. They are not scattered randomly across the cosmos. They are buried deep within these gravitational wells, shielded from our view, waiting at the center like a hidden core. This raises the next great question: what actually happens to matter as it approaches that core? The closer it falls, the stranger physics becomes. And the deeper we look, the closer we get to the Planck scale, the limit where our understanding of space and time begins to unravel. A black hole itself cannot be seen. But what happens just outside its event horizon is one of the most violent and luminous shows in the universe. When gas, dust, or even entire stars wander too close, gravity pulls them inward. Instead of falling straight in, this material begins to spiral, forming what astronomers call an accretion disk. Here, matter is compressed into a thin, rotating structure, circling at nearly the speed of light. Collisions between particles generate tremendous heat, raising temperatures to millions of degrees. At these temperatures, the disk glows fiercely, not in visible light, but in X-rays and gamma rays. This is the paradox of black holes. While the black hole itself is perfectly dark, the region around it can outshine entire galaxies. In fact, the brightest objects we can see in the universe, called quasars, are powered by supermassive black holes feeding on vast amounts of matter. Their accretion disks radiate with the energy of trillions of stars, visible across billions of light years. To appreciate the scale, consider this: the Large Hadron Collider, the most powerful particle accelerator on Earth, smashes protons together at speeds close to light to study fundamental physics. But compared to an accretion disk, the LHC is almost silent. A black hole's accretion disk accelerates natural particles to far higher energies than anything we can build. It is nature's own particle collider, and one that dwarfs human engineering beyond comprehension. And it doesn't end there. Magnetic fields in these extreme environments can twist and snap, channeling matter into relativistic jets, beams of plasma that erupt from the poles of the black hole at nearly the speed of light. These jets can extend for thousands, even millions, of light years, piercing through entire galaxies. What we see through telescopes are narrow lines of energy, carrying the signature of black holes feeding deep in the dark. Despite their beauty, these disks are chaotic places. Particles packed together so tightly crash into one another, heating further, glowing even brighter. The closer they get to the event horizon, the more intense the conditions become. Eventually, all of this matter, no matter how bright, no matter how energetic, is swallowed, disappearing past the horizon into silence. What happens after that is hidden from us. But equations suggest that the collapse does not stop. Inside, the density keeps increasing until we reach a limit, the Planck scale, the point where even our most advanced theories fail to describe reality. This is where the story takes its sharpest turn. Because to understand what might exist at the heart of a black hole, we need to explore the Planck density, the Planck length, and the Planck time, the smallest scales nature allows. And once we go there, physics itself begins to dissolve. So far, black holes have shown us extremes of energy and gravity. But the true frontier lies even deeper, at scales so small that they defy ordinary comprehension. To understand what happens at the heart of a singularity, scientists turn to the language of Planck units. In the early 20th century, German physicist Max Planck introduced a set of natural scales based on fundamental constants: the speed of light, the gravitational constant, and Planck's own constant, which governs quantum behavior. These values define the smallest possible units of length, time, and density, limits where our familiar physics can no longer be applied. Let's begin with Planck density. It is the density at which space and time themselves are expected to break down. It can be expressed with the equation Rp opera C5 opera Hg2, where c is the speed of light, h is the reduced Planck constant, and g is the gravitational constant. At such densities, matter is so compressed that distance becomes meaningless. How small are we talking? The Planck length, 1.6 Xas 10^35 meters, is considered the shortest measurable length. For comparison, a single proton is about 10 to 15 meters across. That means the Planck length is 20 orders of magnitude smaller than a proton. If a proton were the size of the Earth, the Planck length would be smaller than a single atom on its surface. Time also has its equivalent, the Planck time. This is the time it takes for light to cross one Planck length, 5.4 secs, 1044 seconds. It is the shortest meaningful interval of time we can define. Below this, the concept of before and after may not even apply. At these scales, the uncertainty principle becomes overwhelming. You might recall Heisenberg's rule. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. At the Planck scale, the uncertainty is larger than the particle itself. Space, time, and matter fluctuate so violently that the distinction between them begins to blur. This is where the heart of a singularity leads us, to a region where relativity, which treats space and time as smooth and continuous, breaks down, and where quantum mechanics, which deals with probabilities and uncertainties, dominates absolutely. Neither theory alone can describe this regime. This is why physicists believe a new theory of quantum gravity must exist, one that unifies both worlds. But until such a theory is discovered, the Planck scale remains a hard wall. We can calculate the numbers, we can write the equations, but what actually happens beyond this limit is unknown. It is as if nature has drawn a curtain across reality, and behind it, the rules we know cease to exist. In practical terms, what does this mean? It means that inside a black hole, where densities exceed the Planck limit, we are blind. We cannot describe what occurs. All we can say is that matter is crushed into a state beyond imagination, and possibly into a singularity. This is why singularities represent the most profound challenge in modern physics. They are not simply exotic objects out there in space. They are signs that our understanding of the universe is incomplete. The closer we approach to the singularity, the more violent and strange physics becomes. And if the Planck scale is any indication, the energy confined there could be unlike anything we have ever encountered. We have reached the Planck scale, the very limits of length, time, and density. But what does this actually mean in terms of energy? The answer is almost beyond comprehension. Let's start with the uncertainty principle. In one of its forms, it can be written as dH2. Here, dE is the uncertainty in energy, dt is the uncertainty in time, and h is the reduced Planck constant. If we substitute the Planck time, 5.4 x 10^44 seconds, for dt, the calculation tells us that the uncertainty in energy could be as large as 1.96 x 109 joules. That's the energy of half a ton of TNT exploding, confined to the smallest time interval imaginable. But the picture becomes even more extreme when we consider the Planck density. Imagine a cube with sides the length of the Planck length, 1.6 x 10^35 meters. Inside such a cube, the energy could reach 10^113 joules per cubic centimeter. How big is that number? Let's compare it to something familiar. Over its entire 10 billion year lifetime, the sun will radiate about 1,051 joules of energy. But just 1 cubic centimeter of matter at Planck density could contain energy on the order of 10^107 joules. That is orders of magnitude beyond anything we normally associate with the cosmos. Put differently, if you had a sugar cube-sized piece of Planck density matter, it could unleash enough energy to either create an entirely new universe or destroy our existing one in an instant. This is the raw, almost inconceivable potential of a singularity. It is not just dense. It is not just small. It is a concentration of energy so absolute that our physics cannot fully describe it. And this is why singularities command such a mix of fear and fascination. On the one hand, they remind us that the universe contains forces far beyond our control. On the other, they hint at possibilities, that the birth of our universe itself may have been the result of such a concentration. We do not know what emerges from a singularity or what rules, if any, govern its behavior. What we do know is that the energies involved are so colossal, so utterly beyond comparison, that they could change everything we think we know about reality. Which brings us back to black holes. For if every black hole contains such a singularity at its core, then the universe may be filled with countless hidden reservoirs of unimaginable energy, each one wrapped in darkness, shielded by an event horizon, waiting in silence. So what exactly happens to matter once it is swallowed? Does it vanish? Is it destroyed? Or does it feed the singularity, making it stronger with every passing moment? A black hole does not sit quietly in space. It feeds. It waits for anything that drifts too close. Stars, gas clouds, even entire solar systems, and pulls them into its grip. The ancient metaphor is fitting. A black hole is like a vast cosmic web, and at the center of that web lies the singularity, the hidden spider, consuming everything that falls inside. The image may sound poetic, but the physics is precise. Matter caught in a black hole's gravitational well is torn apart and added to its mass. As it grows, its event horizon expands. The more the black hole eats, the stronger it becomes. This is not speculation. Astronomers have measured it. At the heart of our own Milky Way lies Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. Normally, it is relatively quiet, but observations occasionally catch sudden flares of radiation, signs that it has consumed a burst of nearby gas. In galaxies farther away, the feeding is even more dramatic. Quasars, powered by black holes billions of times the Sun's mass, blaze with such intensity that they can outshine the galaxies they inhabit. When we watch these cosmic giants, we are seeing singularities at work. The matter they consume never escapes. From our perspective, it is gone forever, locked away in a realm where the rules of physics collapse. But the singularity inside grows stronger, more massive, more extreme. It is worth pausing to reflect on scale. A black hole the size of a city can outweigh an entire star. A black hole the size of our solar system can outweigh billions of suns. Each one is powered by the same hidden engine, the singularity at its core. The spider analogy is also accurate in another sense. Just as a spider strengthens itself by what its web captures, the singularity strengthens itself by what the black hole captures. It is a one-way process, an eternal trap. Anything that enters contributes to the singularity's gravity, making escape even less possible for the next victim. From a human perspective, it is unsettling. We are used to processes that have limits. A fire burns out, a storm dissipates, a star eventually dies. But black holes appear to have no natural limit. The more they consume, the larger they grow, and the more dominant their singularities become. Some of the largest known black holes are almost beyond belief. In the galaxy TON 618, astronomers have found a black hole with a mass of about 66 billion suns. Its event horizon spans nearly 400 billion kilometers, wider than our entire solar system. At its heart must be a singularity so massive, so dense, that even our most ambitious theories cannot capture its reality. It is a chilling thought that these hidden spiders may lurk in galaxies across the universe, feeding in silence, growing endlessly, while we can only watch from a safe distance. But this raises a question. If singularities are so powerful, why do we not see their effects directly? The answer is that their power is cloaked, hidden behind the event horizon. What we see instead is their indirect influence: the glowing disks, the colossal jets, the warping of stars' orbits. The singularity itself remains invisible. We cannot touch it, we cannot probe it, and we cannot even model it with certainty. And this is where the true danger lies, in its unpredictability. The universe is filled with dangers. Comets streak across space on long orbits, sometimes crossing paths with planets. Massive stars collapse into supernovae, releasing more energy in a moment than our sun will emit in its entire lifetime. Gamma-ray bursts, the brightest explosions known, can unleash beams of radiation across billions of light years. All of these events are destructive, yet they share one crucial feature. They obey the known laws of physics. We can model how a comet moves, how a supernova evolves, how a gamma-ray burst fades. Even if the risks are enormous, the behavior is at least predictable. A singularity is different. By definition, it does not follow the rules. At its core, general relativity and quantum mechanics collapse into contradictions. That means no existing framework can tell us with certainty what happens there or how it might affect the universe around it. This unpredictability is what makes singularities so unsettling. If you were to ask, what happens to matter once it reaches the singularity inside a black hole? The most honest scientific answer today is, we don't know. Does the matter truly vanish? Is it compressed into a state outside of space and time? Or is it transformed into something that could escape into another region of the universe, or even another universe entirely? Each possibility has been proposed. None can yet be proven. This uncertainty sets singularities apart from every other cosmic threat. They are not just dangerous because of their immense gravity or energy. They are dangerous because they are beyond our ability to predict or control. Imagine preparing for a hurricane without knowing how strong the winds will be, or where it will land, or even whether it will appear at all. That is the challenge singularities present. We cannot simulate them. We cannot test them in laboratories, and we cannot observe them directly. They are, quite literally, beyond the reach of experiment. Yet their influence is undeniable. Every black hole suggests one exists at its core. The entire universe may have begun from one. And if new singularities can form, perhaps in extreme conditions we have yet to observe, we would not know until it was too late. It is worth noting the contrast with other cosmic mysteries. For example, gamma-ray bursts once terrified astronomers because of their power. But over decades of study, scientists built models to explain them: collapsing stars, merging neutron stars, and the physics of relativistic jets. The threat could be understood. Singularities remain untouched by such progress. They are not just poorly understood, they are fundamentally outside our theories. This is why many scientists consider them the most serious challenge in modern physics. It is not only about danger, it is about knowledge. Until we understand singularities, we cannot claim to fully understand the universe. So, what could we do with such a mystery? Are singularities simply threats to be feared? Or could they one day be harnessed? If singularities are such unpredictable, destructive places, one might assume they are useless to us. But some scientists have dared to ask the opposite question. What if they could be harnessed? The idea may sound like science fiction, but remember, much of modern technology would have seemed impossible a century ago. The ability to manipulate electrons to power entire cities, to transmit photons through fiber optics for global communication, to split atoms and release nuclear energy. All of these were once inconceivable. Today, they are fundamental to human civilization. So what about singularities? Could we, one day, use their extraordinary properties to our advantage? One proposal is to treat singularities as potential energy sources. The energy density near the Planck scale is so high that even a small fraction of it, if somehow extracted, could outstrip all the power humanity would ever need. Some theorists speculate that if we understood quantum gravity, the still missing theory that unites general relativity with quantum mechanics, we might be able to tap into this reservoir. For now, this remains a dream, but the numbers suggest the potential is real. Another possibility is more dramatic: space-time travel. Einstein's equations allow for exotic solutions, such as wormholes, bridges through space-time that connect distant points. If singularities could be manipulated, perhaps they could serve as the anchors or gateways for such tunnels. In theory, this might enable travel not just across galaxies, but across universes if others exist. This sounds fantastical, and indeed it is. There is no experimental evidence that wormholes or traversable singularities exist. But the speculation is not random. It grows from the mathematics of relativity and the attempts to reconcile it with quantum theory. Even Stephen Hawking proposed that black holes are not truly black. Through a process now called Hawking radiation, black holes may slowly emit particles, shrinking over time until they evaporate entirely. If this is correct, it means that the singularity at a black hole's core is not eternal. It may eventually disappear. Some physicists wonder whether this process could be understood, controlled, or even used. At the moment, these are only ideas. Our knowledge is still limited by the fact that we cannot directly observe singularities. We can only build equations, models, and thought experiments. But history suggests that what begins as theory can one day become practice. 100 years ago, nuclear power was only an idea. Today, it powers submarines, space probes, and cities. The same might one day be true for singularities, though the scale of difficulty is far greater. Still, the possibility sparks curiosity. Could humanity one day turn the universe's most dangerous objects into tools? Could the same singularities that threaten us also become keys to our survival among the stars? For now, those answers lie beyond our reach. But even raising the question pushes us toward deeper understanding. We have followed singularities from theory to black holes, from the Planck scale to unimaginable energies, from fear to speculation. But where does science stand today? How do researchers approach something that seems impossible to study directly? The answer lies in the search for a unified theory of physics. At present, general relativity and quantum mechanics are both incredibly successful, yet fundamentally incompatible. Relativity explains the large-scale universe with exquisite precision, from planetary orbits to the bending of light by gravity. Quantum mechanics explains the subatomic world with equal success, governing everything from chemistry to modern electronics. But at the singularity, the two theories collide. The universe cannot be built on contradictions. There must be a deeper framework that unites them. One leading idea is string theory. It suggests that the fundamental building blocks of reality are not particles, but tiny vibrating strings, existing in multiple dimensions beyond the familiar three of space and one of time. In this view, singularities may not be points of infinite density, but regions where these strings interact in ways we do not yet fully understand. Another proposal is loop quantum gravity. Instead of strings, this theory suggests that space itself is made of discrete loops, woven into a fabric that is not continuous but granular. At the Planck scale, space-time might break down into tiny units, preventing infinite collapse and replacing singularities with something new. Other models speak of quantum foam, a turbulent sea at the smallest scales, where space and time bubble, fluctuate, and constantly shift. In this framework, singularities might be transitions into different states of space-time itself. These are not idle speculations. They are serious attempts to solve one of the greatest mysteries in science: how the universe truly works at its most fundamental level. Physicists know that singularities are more than mathematical curiosities. They are clues. They are the cracks in our current understanding, the places where our theories fail, pointing towards something greater. This is why astronomers build massive observatories like the Event Horizon Telescope, which captured the first image of a black hole's shadow in 2019. It is why particle physicists push colliders to higher energies, probing the limits of matter. It is why theorists spend decades refining equations that may never be tested in our lifetime. All of it is driven by the same goal: to understand the singularity. Because at its heart, this is not only about black holes. It is about origins and endings. The singularity may hold the secret of how the universe began, and perhaps how it will end. It may reveal whether space and time themselves are finite or infinite, whether our cosmos is alone or one among many. For now, singularities remain hidden, silent, untouchable. But science advances. Each new discovery brings us closer to lifting the veil. Until then, we are left with the paradox. The most terrifying thing in the universe may also be its greatest key. A place where all known laws fail, and where, perhaps, the future of physics will be born.